So, Adrian, can you talk to get audio focus?
Yes, Neil.
Okay. Explain what we're looking at.
It's the little axis from Quentin. He created, I think, 2 years ago with modular themes, with the first prototype of modular themes with the SanDisk 11C and the drivers for the 3D printers. And this is the axis that are 3D printed with all.
Okay. Uh, Thank you for sharing that. That introduces today's topic.
It's the minimum machine for this
Yeah,
week.
ab- absolutely. But it did its job of saying hello. So now comes a really interesting stretch. We have two classes that we used to do in separate weeks, but to fit everything else in the schedule, we've merged them into a 2-week unit. So I'm going to cover mechanical design and then machine design. And so in mechanical design, the assignment is to design a machine. That means a mechanism, something moves, actuation, there's a motive force, and automation to coordinate it. And then in the second part, we'll talk about machine design to program it. And to illustrate, if we go back to mechanical design, one of my favorite examples came from the Kerala lab. From Yadu, and I just love this. This is a very clever mechanical clock. So that's an example of the mechanism design. And then in the machine design, the featured assignment, this is a fun video on, this was a 1-week assignment. This is a lathe to trim apples. So this is a apple trimming. It's designed to make custom shapes in apples. And all of this was done in a 1-week assignment. And the reason this class is so important is technically the goal of a fab lab is to make a fab lab. And at the first class, I talked about the stages of 1, 2, 3, 4. 1 is you go, 0 is centralized at a place like MIT. 1 is you go to your fab lab for the tools. 2 is you use the fab lab to make the fab lab. 3 is assemblers, and 4 is self-assemblers. And that's still research further out. But we're just transitioning through the Fab 2.0 stage. If you missed it, the recitation on Monday, this is a portal linking to machines with open designs you can make in a Fab Lab. And posted here is the video. And an amazing group of machine builders who all started in the Fab Academy went on. And so this is a fab in a box. This is a minimal drawing machine. This is a PCB mill that fits in a 3D printer bed. Danielle has a whole team in Germany making open versions of all the Fab Lab machines. Jens is making large format machines. Jake is, I'll talk about this very interesting open control architecture he's developed with Quentin and Leo. Nadia then talked about scientific applications, community impacts. So all of that was in the recitation. So how do you make your own machines? And once again, a machine for today means a mechanism with automation and actuation. And The big difference in this class is it's a group assignment. There's no individual assignment. Together, you're going to work on it, and you're going to divide the tasks. So one person can do mechanism, one could do end effector, one could do user interface software. And as a group, you'll make group documentation. And then as an individual, you'll do separately document what you did individually. And then afterwards, and let me make a note, machine presentations. We're going to do something very challenging during the class after the break, which is we're going to very quickly go around the world and meet all of the machines. And so we'll need to be ready with quick demos and descriptions of the machines everybody made to get through all of them. So, mechanical design. This first part of the class isn't about the active parts. This is just about the mechanisms. So first, a few vendors. In the US, McMaster-Carr makes all the parts I'll be talking about. It's convenient to buy from them. You can generally buy stuff cheaper, more directly, but it's convenient to buy for them for the integration. And so I'll be mentioning them not in particular to suggest you need to buy from them, but just it's a convenient site. Stock Drive is a vendor that has all sorts of precision machine components. Amazon has bought up a number of machine vendors. And so now Amazon Industrial has versions of all the parts we'll be talking about. Misumi is a Japanese vendor that, again, is a really convenient machine building supplier. They have nice versions of all the things I'll be talking about. This is a open site on a reference of materials. There's just a few things you need to know about before we start in detail. For a material, there's a stress-strain relationship. Stress is how you push on it. Strain is how it responds. And a typical stress-strain curve looks like this. This is linear. It deforms elastically. It becomes nonlinear, but it still retraces. If you go further, it starts to flow plastically. At that point, you're deforming it, and so it becomes hysteretic. It doesn't exactly retrace, and then eventually it fails. And so you want the machine building to stay in the linear range is a key constraint. Maxwell, who gave us Maxwell's equations, a famous scientist, did this lovely paper in 1864 where he first makes the point that a structure, something you make, has constraints and degrees of freedom. So if you attach beams like this, if it shears like that, the beams are all the same length. And so nothing really prevents that. So if you made that as a bookcase, it would wobble. But if you make a bookcase like this, but you add diagonals, now it can't, so this can shear, this one can't shear. And so what's going on is there's the number of constraints in the structure, there's the number of degrees of freedom, and you need to have as many constraints as degrees of freedom. If you have more than that, you're wasting material. If you have less than that, the structure becomes floppy. And unless that's intentional, you need to balance that. Hysteresis and backlash is going to be very important. If you have a screw, if you have a nut then that has teeth, if the teeth are touching on one side, but there's a slight gap on the other side, it means when you go in one direction, there's a jump, and when you go in the other direction, you're slightly offset. So the position changes for whether you're going in one direction or the other. And that's bad in machines. And so I'll describe a number of ways you deal with that. Force loops are going to be a key concept. If this is a tool cutting out a part, like one of your circuit boards, it goes into a collet. The collet goes into a spindle. The spindle goes into a z-axis. The z-axis then might go xy axis to an xy axis to this axis. This goes to a bed. The bed then has a platform and then stock, and we eventually get to here. And so it means the position between the tool and the stock is actually determined by this whole pathway from here back to here. And so not the front side of the tool and the stock, but everything on the back side is the force loop. And you want to keep that as short as possible. The bigger the force loop gets, the less reliable the placement of the tool is. Kinematic coupling is something I'll show you when we get to the second part of the class, which is when you remove a tool and you bring it back, you want it to align it accurately but easily. And so a kinematic mount, there are a number of versions of them, but if you look at this example, if you have these 3 slots and these 3 balls, one ball can slide, but when you put 3 balls in 3 slots, there's only one solution. And so even though it seems casual, you just slap this down, when you put it down, you've actually positioned it to say a micron, to very high tolerance. And so that lets you make removable things you can position accurately. And then finally, the last thing is the difference between accuracy and position. If this is a target and you're shooting arrows, if the arrows are all over the target, but they're centered around the origin, the distribution is broad, but the center is correct. That's accurate, but not precise. If all the targets are close together, but they're missing, that's precise, but not accurate. And in the happy condition, you can be both precise and accurate, but there's a trade-off between them. So those are just some general properties of materials and machine design. Now to descend on the mechanisms. Plastic is a material we use. In particular, high-density polyethylene is a very tough plastic. It's used, for example, for cutting boards. It machines easily. That's one of the materials we use for machine building. We can, of course, use a range of metals. We use rubber in machine building, typically for damping and vibration isolation. Garolite is a really nice material to keep track of. Garolite, this is similar to PCB stock. And this sort of garolite, glass reinforced materials you can't safely machine. But this kind of paper or fabric reinforced machines beautifully, but is stiff and strong. Sorry, going back to, yeah, when I described the stress strain curve, stiffness is the slope of the stress strain curve, how little it deforms when you push on it. Strength is the load it handles before it breaks. And so garolite easily machines, is stiff and strong. It's a nice machine building material. Wood, generally we avoid because it can swell with humidity. It can deform. In molding and casting, we'll see these nice casting materials. This is actually really interesting for machine building. because one of the most important attributes in many kinds of machine is the mass of the machine. The weight of the machine ends up being very important. And so rather than machining parts, you can cast parts, and we'll cover that in molding and casting. And then when you need really hard parts and parts that can work at high temperatures, you can make custom ceramic parts by molding these materials from a Remco. And I'll cover that in molding and casting. We tend to stay away from adhesives because you want to be able to disassemble the machine, but we make a lot of use of fasteners. So in large format machining, I described trying to avoid them. In machine building, it's really unavoidable. So the humble nut, there are many kinds of nuts that we use. So there's a basic nut you screw on. When you have a machine with a threaded rod and a nut, the machine is going to vibrate, and that'll make the nut walk, which is bad. And so lock nuts have a little elastic deformation. And so when you tighten the nut, the deformation helps keep it in place. And then a little bit, I'll talk about their more advanced nuts that are anti-backlash nuts that are spring-loaded to prevent hysteresis. For the bolts, we use bolts to attach the machine together. We can use set screws for internal mounts. And then there's more, I'll talk a little bit about threaded rods that we use as motion axes. You need washers when you have something that has to turn against something, like tightening a nut against a load. And then you can also use spring-loaded washers that again prevent nuts and bolts from walking with vibrations. Heat set inserts are handy. If you want to screw into a 3D printed structure, the threads will plastically deform the 3D printing. These are machine threads. You can poke them in with a soldering iron that melts the plastic. The plastic sets around it, and then you can cut into it. Let's see, Leo's asking about Delrin. Delrin isn't a great structural material. It's fairly squishy. It deforms fairly easily. And acrylic isn't great. It cracks. Those aren't happy machine building materials. Rivets are really handy. So a rivet pops a joint between two materials, and in particular, blind rivets you can do from one side. And so if we look at MIT, so in projects in my lab where we've made cellular structures with lots of parts, some of these use little nuts and bolts, but many of these we use rivets. You can get little rivets with a rivet gun, and more conveniently are pneumatic guns, and they let you pop in. It's like a nut and bolt, but just you fire it and it clamps two parts together for fixturing. And so those are some of the joint systems we use in the machine building. Yeah, you can 3D print threads, but again, the problem with 3D printing threads is they plastically deform. And so generally we either have a nut on the opposite side to hold something together, or use a heat insert. When you make the machine, you need to frame it. These extrusions have come way down in cost, and you can get all sorts of kits of parts for these to make joints between them, and all kinds of accessories like wheels. And in addition, you'll see in a little bit, carriages can slide along them. And so these sort of rails are one of the most common ways we frame machines. In what Adrian showed a little while ago, it was a 3D printed rail, which is a fun thing to do, but that's not nearly as stiff, and also it's not nearly as straight as these extrusions. And the cost of those have come way down. You can get plastic channels for framing, depending on the load on the machine. T-slots are the fittings that go in them to make the joint systems. And if you're making your own, you can self-align. So this is an example of, this is HDPE. And this is a very clever joint. The center tab goes in. The shelf there controls the depth that goes in. These feet constrain it. And then these flexures go in and constrain it from the opposite side. So the whole thing snaps together in a very tight joint. And so there's no alignment in the machine. You machine, when you machine the HDPE, you've put in the places for the attachments, and then you just snap the whole machine together. So that's framing. Gears are a surprisingly subtle, huge topic. So to understand why gears are so interesting is, if you take a naive version of a gear, so let's say that's a linear, and then we have a wheel rotating. If you have flat faces, it's really bad, because you go from not touching to all touching to not touching, and it's very spiky. So the most common gear shape is what's called involute, which is a very interesting mathematical curve. And it looks like that. And there's one point of contact. And then as the gear turns, the involute walks around it. So there's always only a single point of contact. So this is a link to all sorts of types of gears from McMaster. Oh, let's see. Yeah, let me, I'll fix that link. Cycloidal gears are, this is Jens's machine, and he actually makes his own rack and pinion. The rack is the long one, the pinion is the little one. He has a different gear shape here that's called a cycloidal. A cycloid is the shape a circle makes when it rolls. The cycloidal gear, compared to the rack and pinion, to the involute,
Neil, sorry, are you sure it's cycloidal? Because as far as I remember, Jens wasn't using cycloidal calculations on the teeth.
No, I'm 99.9% sure it's cycloidal. I'll double check that. I know at this stage in the development, what I'm showing here is cycloidal. I'm not sure if he went beyond that. I'll double check with Jens, but the picture here is clearly cycloidal. And so
no, it's not.
It's not?
I don't think so. But okay, we can double check.
I'll check with Jens. The reason for cycloidal is the involute, when the gear pushes, the pushing is closer to in plane. The cycloidal, the rolling shape, pushes at a higher angle, which is less good structurally. But what's nice about it is there's more clearance in here for the milling machine to get in and make the gear. So the cycloidal aren't quite as good structurally, but they're better mechanically. Yeah, I'll confirm with Jens, but on the cycloidal. So then there are many other interesting gears. helical gears are continuous. In addition to the rolling being continuous, the teeth are engaging, have a more continuous. And then herringbone gears are do that in 2 axes. Let's see if this is loading. And so the Citroën logo is actually from the herringbone gear, which is 2 helical gears, which is at the heart of the original Citroën. So gear design itself is a surprisingly interesting universe. Then beyond a single gear, there are a number of gear families. So a planetary gear is a planetary gear looks like a sun with planets going around it. And those are typically used in speed reducers where the center can turn much faster where it's happy, and then the outer turns more slowly. A rack and pinion is what you saw with Jens, where you have a long axis and then you have a pinion that can run along it for linear motion. To drive gears, these belts, and a GT2 is a typical kind of belt, looks like just a rubbery thing, but it has a reinforcing band through it so that you can bend in one axis, but you can't stretch it. And so that's one of the most common ways that we transfer forces to the gear. Something that I've become a fan of is this is very special string. You can get so think of it as super fishing line. You can get military spec string made out of Kevlar that bends easily, is cheap and flexible, but has very little stretch. And so that's another way to transfer forces. And then with that, what Adrian was showing you was this, which is this is a capstan. And so the motor drives this drum, and then if you wrap the string around the drum, because it doesn't have so the belt has teeth that can go onto a the belt has teeth that can engage, but the teeth can also be slightly discontinuous. The thread around the drum moves continuously, which is nice for smooth motion, but a single wrapping can slip. There isn't enough friction. So what the capstan drive is just does multiple loops to increase the friction between the drum and the belt. And then what's handy is you can just route the string wherever you want through the structure and cut off as much string as you want to do that. And so that's what was running in front of Adrian for the capstan drive. These are hardened shafts that you can move along when I talk about bearings. There are special rods that are threaded rods designed for moving along a shaft. And again, I'll talk about bearing. Then there are special nuts that are elastically loaded. And so they're designed to have minimum backlash when you move them on a threaded rod. Then a really non-obvious thing is a threadless drive. And so let's see. What's going on here, you see those 3 heads at an angle against a rod. There's no gears, there's no teeth, but each of those heads is pushing against that rod, and it doesn't want to drag. What it wants to do is spin. And so when you move that, it makes the equivalent of a threaded motion without a thread to move along the rod. And so that's a threadless drive. And a neat idea is harmonic drives are common in robot joints. And this is something you can buy, but you can also make. What a harmonic drive does is it has a rigid outside, it has a flexible inside, and the flexible inside has slightly fewer teeth than the outside. And then it has this oblong driver. And so each lap around, the inside can move relative to the outside by the ratio that's one tooth. And so that lets you take high RPM motion where a motor is happy and turn it into lots of torque at low RPM. And so these are used very commonly in the joints of robots. And you can make them, and I mean, you can buy them, but it's not heroic to be able to make your own harmonic drives. Okay, so those are ways to get your force into a mechanism. Then we need to guide it. And so again, these hardened shafts give you axes you can go down. And then you can get rails, which are bearings on shafts. And so now we get to the, oh, yeah, sorry, yeah. Then there's one more step before we get to bearings. When you connect your motor to your drive, if there's a slight misalignment between the motor and what you're driving, everything will bind up and can't turn. So these are couplers, and what these couplers do is these ones let you turn at large angles, like 45 degrees, but there's a fair amount of friction. These couplers only have a few degrees of freedom play, but what they do is they're torsionally very stiff, but they give you a little bit of angular play, and they let you deal with a slight shaft misalignment. Then machine building is full of bearings. So ball bearings look like these. There's balls in a raceway. In particular, you can get sealed ones that are designed to have permanent lubrication, where you don't have to do maintenance on them. So if you go back, these are axial. They're designed to rotate, so it lets something turn relative to something else. And we're going to see lots of examples of those when we get to machines. A thrust bearing works in the other axis. A thrust bearing is a vertical load rather than an axial load. A linear bearing is a bearing that moves along a shaft. And I can show you, let's see. When in my lab, when we were testing, yeah, this is shows you the balls in a linear bearing on a screw drive. And so if you look carefully, you can see the balls recirculating. Sleeve bearings are loaded materials that are impregnated that, depending on the load, can be good enough for the lifetime of a machine. Then one of the things that's really revolutionized machine building is skateboards. So these have come way down in cost, these packs of bearings, driven by skateboards and roller skates. And so we make a lot of use of these commoditized bearings in the machine building. And 608 is a standard size for them. We'll see lots of examples when we get to the machines. And then one final note about the bearings, similar to the backlash of you want to elastically load a screw so that it can't jiggle. is if you just take a bearing with no load and you spin it, it's unhappy. The balls can chatter and drag. Bearings are happier when there's a little bit of load on them that makes sure there's good contact between the balls and the surface. And so in good bearing design, you actually design a little bit of preload so that the bearing can't chatter. We use wheels to move things. The most interesting kind of wheel these are omnibot wheels that let you move in more than one axis. And so we'll often see this in wheels driving robots. Generally, the machine building will be talking about we don't need lubricants. Generally, we're using sealed bearings. Cable management is going to be surprisingly important. When you make your machine, there's going to be all sorts of wires and, depending on the machine, plumbing coming in, and you can easily make a tangled mess with it. So cable ties let you tie bundles of cable together. Increasingly, we just use hook and loop. The trade name is Velcro, where you can buy short strips or long tape of these Velcro tapes that let you tie things together. Then those go into carriers. And so these are cable carriers that take bundles of cable and keep them together as the machine moves. A nice trick, you can 3D print, you can buy those, you can 3D print them. You can also use the tape from a tape measure. And if you take a slightly stiff metal tape measure tape and you cable tie to it, it actually makes a nice cable carrier. Let's see, I won't say much about plumbing, but there are standard fittings for plumbing. The one thing I'll mention is for pumping liquids, there's a number of types of pumps, but one particular kind, let's see, two particular kinds. And I'll mention this. So a cycloidal pump is that same cycloidal shape I mentioned, but if you rotate it with a liquid, you can drive the liquid. And a peristaltic pumps works the same way your digestion does. You have a tube and you just roll wheels against the tube. And what's nice about that is you don't actually have to get into whatever the material is. You're just manipulating it from the outside. And these peristaltic pumps are in particular quite easy to make if you need that. Let's see, springs have an important role in machine building for preload. We use those for things like the bearing preload or backlash minimization to have elastic loads in the machine design. And finally, I'm going to end this part with mechanisms are how you take all the things I spoke about and turn them into something moving something. So in the cutting weeks, I mentioned this thesis on flexures, where I showed the example of making an XY stage just by bending beams from this thesis from a while back. So I won't take the time now to scroll through it, but I did that before. With those flexures, you can make a stage. This was an XY stage. Oh yeah, good. So this was cutting out an XY stage to make a flexure. And then building on that, this is a project making very high resolution positioning systems for microscopes, 3D printing flexures. Series elastic is an important concept. The idea of series elastic is if you have a robot and you just drive the legs directly, the robot sort of walks awkwardly. If instead of driving the leg position, you push on a spring, so the motor pushes a spring and the spring pushes on a leg, then the motor is not setting the position, it's setting the force, but the position can change a little bit. And that's how your muscles work. Your muscles don't set the position rigid, they set the force on the joint. And so series elastic actuators let you move more smoothly. Linkages is a vast subject. Linkages is how one kind of motion turns into another one. And so this is a whole gallery of types of linkages. Of you might want to have linear to rotary or elliptical to horizontal. This is all sorts of historical linkages, turning one kind of motion into another one. This is a category of movements that includes linkages with drives, and there's all sorts of types of movements. Again, each of these historically has been appeared to turn one motion into another one. Whippletree is when horses pull a load. If one pulls more strongly than the other, it gets unbalanced. So a whippletree lets you add forces when the forces are unequal. A clever historical design. A pantograph lets you scale things up and down. And so with a pantograph, a small motion can make a big motion, or a big motion can make a small motion. DeltaBot lets you turn linear motion into 3D motion. Hexapod lets you make 5 or 6 axis motion just with linear drives. CoreXY was invented by a student who was in my lab, who had this very nice idea that instead of moving the motors, if you keep the motors fixed and you wind them in this pattern, then if you turn both motors the same way, it moves horizontally. If you turn both motors the opposite way, it moves vertically. And so you significantly reduce the moving mass. And so now most, not all, but somewhere between many and most 3D printers use the CoreXY motion system. Saurus is an interesting idea. If you machine a thin hinge, if you twist it, you'll tear it. But if you don't twist it, you can bend it, and it makes a flap. And so this is actually a motion system that's just based on flaps. And so 3 flaps makes a linear axis. And then this turns all of that into a motion system. Hang Printer does an interesting job of the Maxwell criterion. It's a 3D printer that's hanging, and they've done a lot of work to route the threads so that there's as many constraints as degrees of freedom, so the platform doesn't jiggle, lets you cover a large space. Chuck Hoberman is one of the gods of mechanism design. A colleague who has designed mechanisms from little toys up to structures the size of buildings that fold and unfold. So he makes these gorgeous, massive mechanisms. And the other god of mechanism design makes Strand Beast. Theo Jansen makes these just unspeakably gorgeous walking mechanisms. Let's see, that needs a video. So this is all typically just wind powered. These just gorgeous mechanisms. very, very animate creatures. So that's just a quick tour through mechanical design. And so the first part of the assignment is design your machine. And so, we've had machines that, actually, I'll show this in a minute. I'll show the range of machines in a minute. And then the first task is build the mechanical parts. And then before you automate it, before you drive it with motors or solenoids or whatever you're going to use, drive it manually. You learn a lot up to the very largest machines. You learn a lot by working the machine by hand to feel the forces before you automate it. And so now we'll go to the second half, which is now we're going to add actuation and automation. So bring our machine to life. So this, what I showed you before, this was one of the first Fab 2.0 machines many years ago. From there, rather than making one machine, Nadia and James went on to make these modules that let you assemble machines out of separate modules. So this is making a hot wire cutter. Nadia did a thesis on that, on object-oriented hardware, so physical objects that are simultaneously software objects. And in the Fab Academy a while back, we did a version of that where everybody made cardboard machines, where they made modules. And so that's a 3D scanning machine. Before it was a drawing machine. This is a coffee stirring machine, marble light show machine. This is a hot wire, multi-axis hot wire cutting machine, painting machine. We've had sushi dipping machines, vegetable cutting machines. Just to give you a feeling for see, this was a lathe, the types of machines you can make. That was a ketchup dispensing machine. This is a link to notes. Let's see, let me update the Slocum link. I'll update that link. This is a colleague at MIT who's one of the gurus. He wrote the Bible of precision machine design, and he walks through, in particular, the error budgets. So once you have the notion of the force feedback and the structural loop, how you can work out the tolerance of the joints and come up with an error budget for the machine. We already had the output device class. We're going to have the input device class to cover sensors, which we use in machine building for things like measuring position along an axis, or how much an axis has rotated. For the end effectors, this is Alan, who invented Core XY, and this is Nadia. They did a little machine in a briefcase. Let me go back slightly. You'll see right here, those 3 balls. That's for a kinematic mount. And so here, Nadia's going to snap in a 3D printing head, and the kinematic mount accurately aligned it. And then this machine had multiple heads. So along with the 3D printing head, it had a spindle for milling. It had a knife blade for cutting. And so the end effector is the thing that does the work. And that had modular end effectors. We've covered power electronics already. We haven't yet done networking. In a few weeks, we're going to get up to networking, where we'll cover how to make wired and wireless networks. And in particular, the reason that's important is we're going to talk about machine architectures, and I'll come to that in a little bit based on the networks. This is a machine tool in my shop that is massive and stiff, and nothing ever moves. On the other hand, this is a water jet cutter, where when you're cutting, the whole jet of water is bending as you move. And so what that means is on the water jet cutter, to pick where the jet goes, you don't actually put the head where you want the jet to go, because the jet's moving. You need to actually account for it. So that's a dynamic path rather than a static path. Then open loop and control loop. So you can buy a standard shopbot, and you can buy a alpha shopbot, and this goes from 21,000 to 27,000. And the difference is the open loop, you send the number of steps and you hope everything's okay. The closed loop actually measures its position. And that lets you, if you drive the open loop too hard, you'll miss steps and not be where you thought you were. The closed loop does feedback, which is better, but it's more expensive to implement. And to implement that, now we need control theory. So in this class, I talk about control theory. Here's a whole sequence of, and then this is a link to one of the classic books. Let's take just Adrian's machine. So there's an axis. We have the carriage, and then we have a motor here, and then the motor is driving the carriage. And so the carriage is here, and let's say we want the carriage to go over to there. So very basic task. The simplest thing you can do is, let's say we have a linear encoder that measures position. So we have we can set the current going into the motor based on the position measurement. So the obvious thing to do is you start the motor moving and you turn it off when you get to the destination. That's terrible. The reason is if you turn on the motor and then you turn it off when you get to the destination, two bad things go wrong. When you turn it on, there's a big jerk in acceleration, a big jerk in current. The machine slams and you need a lot of current and the whole machine shakes. When you get to the stop, there's a big deacceleration. The whole machine jerks again. And there's no reason for it to stop perfectly where you want. It's likely to keep going and miss a little bit. So you slam it, you slam it back, and there's vibration and it's poor control. That's called bang bang control. PID has been around for ages. PID stands for proportional integral derivative. So we have two signals. We have where we are and where we want to be. And you can take those two signals and you can get an error signal, and you can use that as part of the controller. But we can, in addition, we can do two more things. And I'll write this mathematically, but you don't need to know how to do calculus. This is a derivative. This is an integral. Just the error term means you have a big control when you start. You slam it on. The derivative term measures the rate of change, and it prevents you from moving too quickly. The integral term, with just the error term, you never actually get to where you want to go because the error is getting smaller and smaller. The integral term builds up the baseline and gets you to where you want to be. And so a PID controller adds proportional, integral, and derivative terms. And so that's better. And you'll see lots of PID controllers. However, there's something better than that that's called model predictive control. And so what model predictive control does is, imagine you're driving on a road and there's a stoplight, and it's currently green, but it's been green for a while, and you know it's going to be turning red soon. You don't stop when you get to the stoplight. You stop long before the stoplight, so you come to a smooth stop. To do that, you have a mental model of your car. And so you're stopping based on your model of the car. And so that's called model predictive control, where you use a model of the machine to figure out how to start and stop based on the machine. Now, to do that, you need the model. You did it by learning over time. And so the most advanced control uses machine learning, and you watch the machine as it's moving, and you dynamically learn a model of the machine that you use to control it. So all of that is what you need. For a little simple machine, you can start with bang bang control, but to make smooth and fast motion, so when your 3D printer is printing really quickly but is quiet and you get nice 3D prints, you need all of this going on to control it. Then comes timing. So let's say we have a machine that has an x-axis, a y-axis, and a z-axis, each of which has a motor. And then all of these are connected to our controller. And so we need to coordinate the machine so that each axis moves in a coordinated way. If they're all plugged into a central controller with one processor, you can do it. But as the machine gets bigger, there are multiple processes. So then you need to use the networking things we'll be talking about to coordinate. And one way to do it is you broadcast over the network a time. You can send times in advance to tell them when things should happen. You can handshake between the processors. And you need all of that when we go to virtual machine control. And so this is one of the most important concepts for today. In a traditional machine, like I just sketched here, let me draw this more carefully. Let's say we have an x-axis with a motor. We have a y-axis with a motor. This is the machine controller that connects to your computer. And then this connects to all the degrees of freedom. But let's say you wanted to add a z-axis, and you wanted to add a rotary axis, and you wanted to add a screw extruder. If your central controller doesn't have those inputs, you're stuck. So instead, increasingly what we do is, if we take here's our x-axis, here's our y-axis, here's our rotary axis. Instead, we connect all of them into a network. So we get rid of the controller and we make the machine a network. And then in software, we talk to the network. And that way, if you want to add something new to the machine, you just add a node to the network. You don't need to change the centralized controller. So Alon many years ago wrote a thesis on that helped start that direction. My student Jake, who's one of the machine builders, wrote a thesis picking up on that. This is a video of one of the versions from Jake where he assembled the machines in hardware, and then in software he makes a graph of the controller, and then the machine control is the software graph. And so we're moving away from fixed controllers and towards network controllers for the machine building to make it easy to adapt the machine. Okay, so next we need to talk to the machine. We've seen lots of file formats. So like G codes that you send to the machine are a common one. Let's see. This is a classic interpreter. So this takes in G codes and then has motor controllers to go to your machine. This is a good example of if this does exactly what you want, it's really convenient, but it has two problems. One is you can't add one more motor. You're limited by what's on the board. And the second one is the G code doesn't understand the machine. It's just a general purpose code. So in this board, you need to explain how the axes relate to each other. And if you change, for example, the gear ratio or the type of mechanism, you have to go back and you have to change the microcode in the controller. And so these are commonly used for predictable machines, but they're frustrating for when you're inventing machines. But that's a standard machine controller. Working back further, you're going to need to build an interface to the machine. So Chili Pepper is an example of an open user interface that lets you send G codes to a machine and interactively control the machine and see what it's doing. Let's see. Universal G code sender is another one. Candle is another one of user interfaces to standard interfaces to machines. Then you need to plan the toolpath. And so let me add a note. So when if you've been using mods, you probably haven't looked at the details, but when you bring in an image, this thresholds it. This finds the distance to the edges. This offsets for the tool size. This finds the edges. This orients the direction. This turns them into strokes. And this accumulates them into the tool path. And then this converts that into what the machine can understand. And so one of the reasons I wrote mods, really the reason I wrote mods is you can open up each of these and see what's going inside of them to see the algorithms. And if you need to change the workflow, you can add or remove modules. Like I needed to put in tabs, so I didn't vacuum up parts, so I added this module. And if you want all of this, but you want a different format, you could change this module. And so that lets you see what's going on under the hood in the path planning and lets you interact with it. Then you need to describe you need a geometry representation of what you're going to make. And let's see, docs, theses. Matt Keeter wrote a nice thesis. I'll put that link in, where he talks about the mathematics of representing design geometry. And finally, we're ready now to make our machine. So that's walking back through the stages of what's going on in the machine. So now I'll talk about lots of examples. Open builds, robot shop, O-Drive, all are versions of, you can buy complete finished machines from them, and you can buy all the parts to make machines. So these are vendors specifically for machine building. Then these are all motor vendors. And so these all have all of the different flavors of motors I've described, like stepper motors. I described for torque at low RPM, you need a gear stepper. If you want to know position, you need to do feedback on it. So these are examples of all of the motors. So these are all motor vendors. And one of the things to know is, thanks to our friends in Shenzhen, they can very easily customize your motor. Not for a single one, But if you want a motor of a certain package size with a certain torque, given a given step size, and if you want, for example, say an integrated lead screw with an anti-backlash nut or whatever fittings, once you get up to 10, even 10 motors, it's surprisingly accessible now to have order custom motors from those vendors. Okay, next come so Pololu as an example will sell you an individual motor controller. It'll sell you integrated arrays of motor controller boards. These are all, Synthetos is, I'll fix that link. These are all different versions of standard control boards. So these are widely used in open source communities. These are standard general purpose motor control boards. Then Danielle, Fab Academy student turned instructor, turned machine builder, along the way developed a whole line of fabbable control boards designed to be produced in a fab lab. And so there have been multiple generations of, that was Danielle's, here's Jake's motor controller designed to be mounted on a motor. Here's a version Quentin did, all designed to be made in the fab lab. Then we get to these two projects I want to spend a little while on. So a rumbu, this is a paper on a rumbu. And this is, I got interested in how simple we could make motor control. And so I'll play a video here. So the motors are all moving, and the tones you hear are the stepping. And so I'm stepping at audio frequencies, so reasonably fast stepping rate. And what I'm doing here is ordinary USB 3 will give you up to about an amp, and you can negotiate above that. But an amp is enough for a motor like this. And ordinary USB 2 will give you 10 megabits. So in a rumbu, what I'm doing is the motor controller doesn't know anything about G-codes or anything. All it knows how to do is make one step. And then in software, I'm very quickly sending it steps as USB packets. And so from there, this was an example where, with two of them, I made a drawing machine. And then with, this was turning it into XYZ machines. So this was making multi-axis machines. And so a rumbu is the simplest of all of these. Then that inspired the Modular Things project. And so Modular Things is a little bit, so in a rumbu, there's no information at all. All a stepper knows how to do is step. A rumbu is based on a USB port per module. And so we use USB hubs as the power supply, and you need as many USB ports as you need modules. And that's all a rumbu is trying to do. To Ricardo's question, Modular Things was inspired by that, but is based on simple modules that are a little bit more powerful, that know what they do, that makes it easier to write the software. And in particular, Modular Things can use multiple network protocols. So it's not just USB, but it can use other networking protocols. And I'll update, if we go back to the recent recitation, Jake, Leo, and Quentin now have these versions of fabbable modular things modules. And then they have this software environment that you use to write code for them to coordinate them. And so somewhere between Arumbu and modular things, let's see. Adrian is putting this example in the chat of a modular things. This is a core XY. So yeah, this is showing many of the things. This is showing the high strength thread routing in the core XY geometry using modular things to make a core XY motion system. So all of these are recommended ingredients. Then from there, this is a site for, I periodically teach, and I'm currently teaching a machine building class at MIT, taking this last hour and unpacking it into a semester. Clank are machines from Jake, Jubilee from Nadia, Felish Werkstatt from Jens, Open Lab from Danielle are all families of machines. These are all commercial machines that spun off from Fab Labs. And finally, these are two fun machine builders that make machines that are not in any way useful, but that are always interesting that you can browse. So that was a big tour. Again, in the machine building class, we're doing all of this filling a semester, and we just did this in an hour. So the goal of this week is not to become a master of any one of these things, but the goal is for you to see all the stages, from the low-level electronics, from the mechanism to the electronics, to the microcode, to the communication, to the coordination, to the interface, for you to see the whole stack, how it comes together. Looking ahead, we have a sensor class to come. We haven't done that yet. We have the networking class to come. We haven't done that yet. And we have the user interface class. So all of that we haven't yet covered, but your lab will have examples. And what I want you to do is, as a group, come up with a machine, mechanism, actuation, and automation. Build it and program it. As a group, make group documentation, individually cover what you did. But for this week, unlike what I've said for final projects, you can segregate. So one person just does user interface. One can just do motor control. Each can do a particular task. The assumption is the collaboration is in your lab, but it's fine to collaborate between labs. You can work between labs on the tasks. And then what we want to be ready for is in 1 week, there's no class. We're going to be on break. In 2 weeks, we want to see all your machines. And so to do that in the first half of the class means we can only spend a minute or two per lab, really fast. But for each lab, I'm going to click on your site. And on your site, I want to see a link to the machine that I can go to quickly see what your machine is. So you each have a to-do to get your group sites ready with a link to the machine. And we'll do a round-the-world tour to see all of your machines over this 2-week break. And so that's a 2-week group assignment. And then over the break, the other assignment we'll be doing is checking in on your individual project progress to keep you moving. So this is a creative, fun week. It's a lot of work. It's a sprint, but it's one of the most rewarding weeks. You'll come out of this hopefully understanding your machines, and in particular, really driving this transition of come to the Fab Lab not to get access to the machines, but to make your own machines, and to drive this transition to rapid prototyping of rapid prototyping. Okay, open time will keep running. And with that, I eagerly look forward to seeing all of the machines you make. Happy machine building. Bye-bye.
Hey, hey.
Chao.
Hasta
Luego.
Goodbye.
Chao, chao.
Bye.